The broadcast is now starting. All attendees are in listen-only mode.
All right, welcome everyone. My name is Amanda Sheffield, and I am the Regional Drought Information Coordinator for NIDIS in California, Nevada. Welcome to the May California, Nevada Drought and Climate Outlook webinar. Thanks to those that have joined us previously and those who may be joining us for the first time. This webinar series is designed to provide the region with timely information on current drought status, associated impacts, as well as a preview of developing climatic events. This webinar is being recorded, and along with a two-page summary will be available on drought.gov and the drought.gov YouTube channel later this week. For those who have been with this before, we have our usual drought and climate update, but we do have a little bit of a special webinar this time. I'll talk about that a little bit later, but we are co-hosted today with the Modeling Analysis, Predictions, and Projections program from NOAA, or the NOAA MAP program, and you'll learn a little bit more about them later and why we have them on the webinar today. Just a little background for those that don't know what NIDIS is, or the National Integrated Drought Information System. We provide a better understanding of how and why droughts affect society, the economy, and the environment, as well as improve accessibility and use of early warning information for drought risk management. To do this, we've been building off a network of regional drought early warning systems to create a national drought early warning system and work with key partners and existing partner networks in the region, from federal, tribal, state, local, and academic partners. This way we can try and make climate and drought science impactful and readily usable, available, and things like that to improve the capacity for planning for drought. If you're interested in more information, visit the drought.gov website and go to California, Nevada, or you can contact me and talk about our strategic plan or the quarterly key stakeholder calls we have and things like that. As I mentioned, today's a little bit of a special webinar that we have today. So after we do the normal drought and climate update and outlook, we're going to highlight a story map co-created by NIDIS and MAP on the last California drought. With us, we've got quite a few different speakers from different backgrounds with NOAA and different agencies and labs and things who will talk about all the different pieces in the last drought, as well as water resources and management in California, Nevada. As I said, MAP's our co-host today, and I'd like to introduce first here Allie Stevens. She helped put this map together and did a lot of the legwork pulling it together, and she's a communications specialist with the MAP program. And with that, I want to give her a chance to talk a little bit about what MAP is before we go into all the details.
Thanks, Amanda. Hi, everyone. As Amanda mentioned, I'm Allie Stevens, one of the creators of this story map, and I'm also a communication specialist, or technically program specialist, for the Modeling, Analysis, Predictions, and Projections program, also known as MAP, which is a competitive research program in the NOAA Research Climate Program Office. And MAP's mission is to enhance the nation's and NOAA's capability to understand, predict, and project variability and long-term changes in Earth's system to help prepare for and mitigate human and economic impacts. And we do this through funding 2 to 3 year projects that support foundational research, transition to research applications, and engagement across NOAA and with other agencies, as well as with the external research community. And MAP's current research and development projects are currently addressing 4 application areas, including drought and water resources, climate extremes, fisheries and marine ecosystems, and coastal flooding. And to better address these application areas, as well as MAP's mission, MAP organizes task forces, such as the Drought Task Force, which is composed of scientists funded by MAP and NIDIS. And so some of the Drought Task Force's research is highlighted throughout the story map, which we're going to show you later today. So that users can learn more about the work that MAP and NIDIS are supporting to better monitor, understand, and predict drought. And since this was a very brief overview of MAP, if you want to learn more about MAP, go to cpo.noaa.gov/map. And to learn more about the Drought Task Force, go to cpo.noaa.gov/map/DTF.
Great, thanks, Allie. With that, we'll get into the knee-deep into these topics here. Our first talk is going to be by Dan McAvoy. He's a climatologist with the Western Regional Climate Center at the Desert Research Institute, and he's going to be giving us the drought and climate update and outlook.
All right, thank you for the introduction, Amanda. Let me see if I can get my screen up. Let's see. Do you share that with me, Amanda?
Yeah, you should be. I passed control over to you. Do you see it?
Oh, let's see here. It's freezing. Hold on one second. Sorry for the delay. The WebEx is frozen. No.
Do you need to hop on and hop off real quick, Dan?
Well, yeah, I might need to start it over. Sorry, it's looking like it wants to cancel. Let me do that real quick.
Hop back over here. I realized too a little bit, I think while we were talking over it, we still had some of the slides paused. So here I just wanted to highlight the map slide that Allie was talking about. I apologize that I think you guys might not have been able to see that while Allie was talking.
I'm reopening the webinar. Sorry, it
Great.
doesn't want to open right away.
While we're waiting, Allie, do you want to introduce some of the other speakers so they'll save some time later on?
Sure. So you guys can see Michelle LaRoe's info card right now. So Michelle is a meteorologist with NOAA's Climate Prediction Center. And her primary responsibility is to coordinate a team that updates the official status and forecast for the El Nino Southern Oscillation, or ENSO. So she'll be talking about ENSO a little bit later. We'll also have Dennis Lettenmeyer, and he's a distinguished professor of geography at UCLA with interests in hydrological modeling and prediction, hydrology, climate interactions, and hydrologic change. And he is also part of the California-Nevada Application Program, or CNAP, which is a NOAA RISA team, and is also one of the co-leads of the MAP Drought Task Force. And so he'll be talking about the droughts progression, the California droughts progression.
Looks like I'm back.
Allie, you just want to do Marty's real quick, and then we'll switch back over to Dan?
Oh, sure. So Marty Hurling is a research meteorologist with the Attribution and Predictability Assessments team at the NOAA Earth System Research Lab Physical Sciences Division, and he's also former lead of the NOAA Drought Task Force. And so later today, he'll be talking about some of the causes of the California drought, as well as the relationship with climate change.
Okay. Dan, did that pop over to you?
Yeah. So are you seeing my screen yet?
Yes, we see your email.
Sorry about that.
There we go.
Okay. Okay, it's on the wrong side. Okay, you're seeing the wrong side, aren't you?
Yeah, we see the presenter version.
Screen 2. Okay, is that good?
Yes, thanks. You're good to go.
Okay. My apologies, everyone. Sorry about that. Here we go. I'm going to go through the climate, the drought update and outlook. No more introductions here. Let's get right into it. So this is the latest U.S. drought monitor map from last week. And what we see here in California, Nevada is once again, we have quite a bit of drought creeping into the southern part of both states. And this is part of a much larger drought over the Four Corners region. You can see the D4 in that region. But this really intensified quite a bit over the past year. And another thing to note is parts of Southern California now have not been drought-free. They've been D1 or greater going all the way back to 2012. So this is a really long ongoing drought. I think it's gotten a lot less attention since our big winter in the north last year, but there's still a very persistent drought in the southern part of both states. And I want to show the change map next. So this is the change over the past 6 months from early December. And we can see that there's 2 and 3 class degradations over the course of the past water year, particularly in Southern California, where there's 3 class degradations, as well as South Central Nevada, where there's been 2 class degradations. And so this is driven by what we saw this past water year for the most part. And so what I'm showing now are the water year precipitation and temperature percentile rankings. So this is October through April from the West White Drought Tracker. And on the left we have precipitation. And so what we see is that there's a bit of a gradient, but the southern and eastern parts, particularly southeast Nevada and Southern California, were very dry this winter again. Almost the entire southern parts of the state were in the bottom 10 percentile, going all the way back to 1895 based on PRISM. And a few locations saw record dry October through April. Now, as you move further north, there was quite a bit more precipitation. The northern Sierra and the western Great Basin were actually above normal for October through April precipitation. If we shift over to the right to temperature percentiles, pretty much unanimously across the whole region, temperatures were above normal. And a lot of regions saw top 10%, and a few locations to the south saw record warmest. So the combination of record warm and very dry conditions led to that re-intensification of the drought in the south. I also want to talk about May, which has been pretty interesting. So this is the latest May precipitation and temperature anomalies. On the left, we have preset May 1st through the 26th, and this is the percent of average based on GridMet, and this map was created using Climate Engine. And so we had a series, about 2 weeks, that just ended a couple of days ago, a series of cutoff low pressure systems that sort of came over the Great Basin and stalled for a couple of days at a time and dropped quite a bit of precipitation. There's a sharp gradient though, so interior in the Great Basin and the east side of the Sierra Nevada, well above average precipitation for the most part for May. Then to the west of the Sierra Nevada into coastal California, things have been still quite dry through May. And temperatures were above normal to the north, and southern and coastal California have actually been below normal. But this rain in the Great Basin, it's not going to do a ton to change drought conditions other than really moisten the soil moisture for a few extra weeks probably, which is good. But it's also going to lead to conditions ripe for growing fine fuels and cheatgrass and lead to fire conditions for the Great Basin, which I'll talk more about in a bit. I wanted to talk about the snowpack. We're getting to the end of the snow season, but so this is now the northern Sierra and Nevada snowtail basins, percent of normal snowpack for May 29th. Most of these basins climatologically still have a little bit of snow this time of year, and they tend to melt out the end of June to the middle of June. Lake Tahoe Basin has no more snow left. Most of the Humboldt Basin region has well below normal snowpack, and this was driven by a combination of the low precip as well as the warm temperatures during the snow events. You notice the Truckee Basin and the Walker Basin are actually quite a bit different. They have a couple of higher elevation locations that actually did get a bit more snow due to the elevation gradient, which I'll talk about in a few slides. And so, but they're still well below normal at about, close to 60% of average. Similar situation when you consider the California basins that were not included in that previous graphic. Statewide, as of May 24th, the California basins were at 12% of normal. So not a good snowpack year. I wanted to show a time series. This is just to point out a couple of features. This is for the Lake Tahoe Basin. So this is all the snowtail sites averaged throughout the Lake Tahoe Basin. And the black line was this year. And so we had a really poor start pretty much through the heart of about half of the winter or more. And so you see up through the end of February, we're very far below normal, approaching record low. We were neck and neck with 2015 at the end of February for lowest snowpacks on record. Then we had a very large, wet and actually cold March that brought a lot of snow. The term Miracle March got thrown around a lot, and I was calling it a miracle-ish type of March because it greatly improved the snowpack, but we didn't really get close to average at all. And you'll see that after that, we had a big storm in early April, with high snow levels, didn't do much for the snowpack, and so ended up melting out in the Lake Tahoe Basin about 2 to 3 weeks early. So overall, a pretty poor snow year for the Sierra Nevada. And then I want to talk a bit more about the elevation gradient. And so what I'm showing now is, so this is again for the Lake Tahoe Basin. On the x-axis, we have the April 1st % of median sweep from the snow courses in the region. And then the y-axis is the elevation of those locations. And then the dots are actually colored by the % of median precipitation, which is the color bar there. And so a few things to point out here. You'll notice all the dots are in that white color, indicating that in the region, the precipitation wasn't too far from average one way or another, somewhere in between 80 and 120% of normal precipitation from October through March. Yet there's a big gradient in the snow water equivalent, with the lower elevation stations below 60%. Most of the stations were sort of in between the 60 to 80% of normal April 1 snowpack, but a lot of them were less than 70%. And so once again, we saw this warm snow drought in the Sierra Nevada where precipitation was not too far from normal, yet the snowpack on April 1, particularly at the lower elevations, was in very, very poor shape. And so this is something to consider when we talk about the water supply, which I'm going to be talking about next. First, I wanted to mention the reservoir conditions. And so on the left, we have the current California reservoir conditions as of May 24th, and the time series of the Lake Tahoe elevation and Rye Patch Reservoir elevation on the right. So overall, the reservoirs are actually in very good shape. A lot of this is due to the carryover we had from last winter with the near record-breaking or record-breaking precipitation in parts of the Sierra. And even in the south, in California, the reservoirs are in pretty good shape. But I did want to highlight a few things here with the two time series on the right. So most people know where Lake Tahoe is, which is on the in the northern Sierra Nevada, but Rye Patch is out in north central Nevada, and the Humboldt River Basin, which is a very large river basin in northeast Nevada, drains into Rye Patch Reservoir. And so right now, both reservoirs are near full. Lake Tahoe is pretty much at full brim, and so is Rye Patch here. But I wanted to point out that in the previous drought in the northern Sierra, Lake Tahoe took 3 to 4 years to kind of get to those low to critical levels due to the very large size of the reservoir. So it took a while to respond to the drought. But Rye Patch Reservoir, on the other hand, had one dry year in 2012 and went from really good shape to nearly empty by 2013. And so a much quicker response time to drought in those smaller reservoirs. And so that's something to keep an eye on, especially considering the stream flow, which I want to talk about next. And so this is from the California Nevada River Forecast Center. This is the observed water year stream flows. This was through May 25th. And this is pretty interesting. A couple things to point out here. First of all, the central and northern Sierra, the stream flows for the water year have not been too bad. They've actually been above average in a lot of cases until you get a little further down on the west slope, get a little bit below average. But this wasn't due to a really large winter. This was more due to carryover from the previous winter, where the mountain block and the groundwater actually stayed filled and basically carried over into this year. And so the streams were running high all winter long. Now, when you shift out of the central northern Sierra, conditions are a lot worse. The north coast, central, south coast, southern California, very low water year stream flows, much to extremely below normal. And then the Humboldt Basin out in northeast California or Nevada that I was talking about before, also pretty poor water year stream flows due to low precip and low snowpacks, like I was showing before. So I wanted to transition then into the outlook from there, starting with the water supply outlook for California and Nevada. So this is a similar map, except this is now showing the forecast, the ensemble stream flow prediction forecast for April through July total stream flows. So the percentage expected of that total volume percentage of average. And so again, the northern and central Sierra Nevada, The forecast isn't too bad. There are a lot of locations forecast to be slightly below normal. It gets a lot worse when you get down into the southern Sierra. The very south end of the Sierra is forecast to be less than 50% of normal stream flow. But again, this area to really keep an eye on for drought development, I think, is out in northeast Nevada in the Humboldt Basin. As I mentioned, the reservoirs are much smaller out there. And so if they get a very poor stream flow year, 30 to 50% of normal, I think the reservoirs are going to be dropping quite a bit by the end of the summer. And we may need to consider moving some drought conditions into northeast Nevada. So I wanted to show the CPC 3 to 4 week temperature and precipitation outlooks for a couple of reasons. One reason, these shorter term outlooks are more skillful, meaning there's more reliability, and you can use these a bit more in terms of planning and have better confidence that the forecasts will be better as compared to the longer term seasonal, annual type forecasts. And another reason is for development of fire danger conditions. And so this map's valid June 9th through the 22nd. And on the left, we have the probabilities for temperatures. And so pretty much the entire California, Nevada region, except for parts of the central and south coast, are forecast to have higher probabilities of above average temperatures. And on the right, we have precipitation. There's not a huge signal, but to the north, it's forecast to have higher probabilities of below average precipitation. And so what's concerning here, as I mentioned, in the Great Basin, we had all that rain the past 2 weeks, and the fine fuels have really taken off. The cheatgrass is going crazy. I'm here in Reno, and the hills are covered in a fresh coat of cheatgrass right now. And we could see that, and we probably will see this flash drying of the fine fuels in the Great Basin, and doesn't take much. It takes a few weeks of above normal temperatures and dry conditions to really cure those fine fuels. And so that's going to lead to above normal fire danger conditions in the Great Basin going into mid to late June. As we go into July, things will really start to pick up for fires in the Great Basin. Next, I wanted to show the seasonal outlook. So this is again from CPC, and this is the June through August outlook. The forecast was made on May 17th. And so on the left, we have the temperature probabilities, and then on the right, precipitation. We could start with temperature, and this is basically showing that there's a pretty strong signal for above normal temperatures in California and Nevada for the summer. The signal is a bit stronger in eastern Nevada, but overall, it's a pretty strong signal with a lot of areas having a greater than 50% chance of above normal temperatures. For precipitation, it's much less clear. There's equal chances of above or below normal precipitation for the region for the summer. This is climatologically the dry season, so the precipitation forecast really isn't as important. Although I will note there is slightly higher odds of above normal precipitation over the Four Corners, which is a monsoonal signal for an increased monsoonal activity. But the monsoon is one of the hardest things to predict, especially at that lead time. So I wouldn't, I'd take that forecast for precipitation with a grain of salt for the summer precipitation forecast. I also wanted to show the National Significant Wildland Fire Potential outlooks. These are put out by Predictive Services, and they show areas that have the potential for above normal wildland fire activity. And so we have June, July, and August. First we'll look at June, and as I mentioned, the Northern Great Basin is in red for above normal potential in California, and Southern California, I think, has been in that red possibly for over a year now. I'm not quite sure if it ever came out of that above normal potential, but still high fire potential in parts of California. So moving to July and August, things shift a little bit more to the north for high fire potential, and then again to the Sierra Nevada once the timber starts to dry out, and also more to central coastal California, not just Southern California. So there is very good chance of another very active fire season in the region this summer. I wanted to briefly talk about the ENSO forecast, so the El Nino Southern Oscillation. I didn't want to spend too much time on it. We've transitioned out of our sort of weak La Nina from last year into ENSO neutral conditions. And so this is a forecast from the IRI and CPC showing the probabilities going through several seasons out into next fall and winter, the probability of being in ENSO neutral, La Nina, or El Nino. So if we focus first on the first couple of seasons, that there's very high probabilities of being in ENSO neutral going pretty much through the summer. Even through July, August, September, there's still above 50% chance of being in ENSO neutral. Things start to change as we go into the fall and winter, and the forecast scale at this time of year is not that great for next fall and next winter. And so I think this forecast will be much more valuable in the next webinar in July, but I will mention that many of the forecast models are pointing towards a transition to El Nino, although there is quite a bit of model spread. And the strength of the El Nino being forecast, which isn't shown here, is quite weak this time. But as you get out into the fall and winter, the probabilities increase to above 60% chance for transitioning to El Nino, which here in California and Nevada, we feel the biggest impacts of ENSO during the fall or during the winter and spring. And so these ENSO forecasts will be much more valuable when we get into the late summer. We have a little more confidence in what ENSO is going to look like. Finally, I just wanted to show the seasonal drought outlook from CPC. And if we focus in on California and Nevada, not surprising, going through the summer, our dry season, drought is expected to persist where there is currently drought in Southern California and southeastern Nevada. This forecast does not show any drought development to the north, but I'll likely be chatting with our regional group about potentially introducing drought to northeastern Nevada due to this poor snowpack, low stream flow, and likely degrading reservoir conditions. It would be great to get some impacts from that region out there if they're seeing any this summer to help sort of assist in if we need to change any of the drought categories out in that northeast Nevada region. And I think that was all I had. So sorry about the technical issues in the beginning, and thank you very much.
Great, thanks, Dan. At this time, if anyone has any questions for Dan, feel free to type those in. I'm going to change over to the next speaker, but we can get a few of those in while we're working on this.
Okay.
All right. Well, I don't see any questions yet, so Allie, I'll let you go ahead and get started.
All right, great. Amanda, can you see my screen?
Yes.
Okay, perfect. All right, everyone. So we're really excited to show you this new product that we've worked on. It's been a long time coming and a lot of work involving a large team. But before we walk you through the story map, we thought it might be helpful to answer the question, for those of you who don't know, what is a story map? So a story map is an interactive web app developed by Esri that allows you to combine interactive maps with multimedia content like photos, videos, and text to tell geography-based stories. And what's great about story maps is that they are a really compelling method for communicating complicated information, science, and data, and they help make this information more accessible and engaging to a broader audience. So for instance, a major challenge of talking about drought, its contributing factors, and its impact and causes, the topic of today, is that it's all interconnected, and the science behind drought is very complex and interdisciplinary. So the story map allows the connection of all these complex pieces, combining data with interactive elements and relatable images to create a well-rounded, informational, and interesting piece of science communication. And then also, before we really get started, I wanted to point out a few key features of the story map that we don't want you to miss as you explore the story map on your own. And feel free to click through the story map while we're presenting it right now. So first, this header at the top here allows you to jump around to different sections of the story. There's a lot of content in this story map, so you may not want to read it all, or you may want to jump around to revisit a particular section. Let's see. We also have interactive web maps like this one here, where you can use your mouse to click around. You can also open pop-up boxes like this one here. And you can also zoom in or zoom out to focus on areas of interest to you. And then we also have animation and videos like this one shown here that provide additional information. We have interactive sliders like this one on Snowpack that show different time comparisons. We have photographic evidence of the drought. And we provide links to more information and resources throughout the story map, as well as a list at the very end of the story map that I'm showing here so that you can learn more. And then finally, we highlight MAP and NIDIS-funded research throughout the story map. And so to get you all thinking a little bit about the 2011 to 2017 California drought and future droughts, we wanted to ask you all a question. And so Amanda's going to start a poll, which she's showing here. And we'll come back to this question and the results towards the end of the story map when Marty speaks.
Thanks, Allie. So yeah, we were putting together the story map and talking about it. We were thinking about different people have different ways they think about drought, how drought impacts them. And so we thought as we move through the story map, we'd ask you, when did the drought end for you? Thinking about, was it when we had some precip in 2016, when the governor lifted the proclamation? Is it still going on for you? So some of this is the questions we're asking here to help try and steer some of the ideas we're doing later. So I'm going to leave this up here for a minute, and then we'll go ahead and get started a little bit with going through the story map, thinking about the history of drought in California, the water resources, how we manage water, work through the drought progression of it, and then think about the causes and climate change and some of the great work that's been done. And you'll have that from the speakers. I'm going to give a little bit more time and pass it back then to Allie to go ahead and get started with history. Okay, I'll close that, and Allie, back to you.
Thanks, Amanda. Can you see my screen right now?
Yes.
Okay, great. All right, so now we're ready to walk you guys through the story map. Starting with a very brief background, and Marty may talk about this more later, but as I'm sure many of you know, California is no stranger to a lack of rain and dry ground. Since 1895, the state has suffered through several extended periods of dry weather, with its driest 3-year period based on the calendar year from 1974 to 1977. However, California has also been soaked with extended periods of wet weather, such as during the mid-1990s. And one quick note here, since we are using the calendar year, some of the dates mentioned in the story map may differ from dates based on the water year, which is the 12-month period from October 1st through September 30th of the following year, and is designated by the year in which the 12-month period ends. So just something just to keep in mind as you scroll through the story map. And this image here that we're focusing on shows a percent area of California affected by each of the drought categories for the 2011 through 2017 California drought. So given this setting, we asked the question that you can see here in the story map: how does the 2011 to 2017 drought fit within California's history? And so we try to answer this question through this story map, and our speakers may discuss this more today. So to get into the story about what happened during this drought, we need to talk about where California gets its water from in the first place. So we're going to move into water resources. So California gets its water from a variety of interconnected sources that we talk about and visualize in this section of the story map. Starting with its reservoirs, California has almost 1,300 reservoirs that help capture and store precipitation for use during its dry summers, and they help with flood management for major rain events. And here in this map, we're showing the 12 major reservoirs. And if you're exploring on your own, you can click on the pins here, and then click on the thumbnail image in each of the pop-up boxes to see current reservoir conditions. So this one here is showing the reservoir conditions for Pine Flat Reservoir. So moving on, in addition to the 1,300 reservoirs, California's Snowpack acts as another reservoir in the mountains and stores about 65% of California's water supply. The snow melts throughout the summer and helps replenish California's reservoirs. And then contributing to this snowpack are extreme events called atmospheric rivers, which I'm sure many of you are familiar with. And they provide about 20 to 50% of California's average annual precipitation. So you can think of these as rivers of the sky that are narrow regions of strong winds and lots of moisture in the atmosphere that help transport water moving from the Pacific Ocean to California and can dump tons of rain and snow on the state. So they really are a blessing and a curse because they can substantially support California's water supply, but also cause damaging flooding. So we're going to skip this next one for now and come back to it when Michelle speaks. But another really critical water resource, especially when California's surface water becomes limited, is California's groundwater. So during a dry year, groundwater provides about half of California's urban and agricultural water supply. And similar to the interactive reservoir map, you can click on the pins in this map to learn more information about a few of California's groundwater wells. So now we're going to switch to Michelle, who's going to walk us through the last water resource that we described in this story map. And so I'm going to move to that section. All right, Michelle, are you there?
Yes, I am. Thanks so much for having me. So what is being shown here are two images of essentially, I think it's either sea level height or sea surface temperatures, actually it's sea surface temperatures. And what it's focused on is the tropical Pacific Ocean. That's important because as one pattern that can help drive rivers and other precipitation or rainfall events is the El Nino Southern Oscillation, or ENSO. And the warm state of ENSO, shown on the left panel there, is El Nino. And as seen by above average sea surface temperatures over the central and eastern tropical Pacific Ocean. And the opposite state is La Nina, which is characterized by below average sea surface temperatures. You can go ahead to the second slide. And this image is showing sort of the overall pattern, the flow and the temperature and precipitation departures that you get with El Nino, which is that warm state. And El Nino is usually associated with the extension of what we call the Asian Pacific jet stream, which is a river of air that flows from west to east over the North Pacific Ocean. And during El Nino events, because of all this warming in the tropics, this jet is very energized and it extends farther eastward than it normally does. In fact, it goes across the whole southern tier of the United States. And what this helps facilitate is sort of bringing above average precipitation over the southern United States. Now, with that said, this is showing the typical average wintertime pattern. And no El Nino is exactly like another El Nino. There's still a lot of variation from El Nino event to El Nino event. So, for example, the strong El Nino events in 1987, 98, and 1982, 83 led to considerable rainfall and flooding over the West Coast in California, but an equivalently strong El Nino in 2015-16 did not lead to drought-busting rainfall that people might have otherwise expected. So the lesson from this is that climate forecasts have a lot of uncertainty, and El Nino is really just one piece of that puzzle. Also, in their research, scientists are still trying to understand how different types of El Nino events may result in different impacts over the United States. And a good example is what's shown in this link. If you're going through the story map, there's some map-funded research by Jaime Kim and others, which says exactly where the sea surface temperatures warm up in the tropics, whether it's more in the central Pacific or the eastern Pacific, could influence the position of the jet stream and also the location of where rainfall occurs over the western United States. All right, if you go now to the third slide, our La Nina pattern. So remember, as I said, there's the warm state, which is El Nino, and there's the cold state, which is La Nina. This is showing the average La Nina pattern during the winter months. And La Nina will often lead to less precipitation over the southern part of the United States. And the reason for this is that there's usually a really big blocking ridge over the North Pacific Ocean, which will essentially hinder the flow of the jet stream. Remember that river there moving from west to east, it will kind of get blocked up, stopped up. And what happens is it diverts usually farther northward. So you get fewer storms being steered into the southern west coast. And so it's not bringing in that moisture off the ocean. And again, I want to emphasize this is not a sure thing. We're looking at statistics here, and usually when you look at the average of all La Nina events, that's what this pattern looks like. But there are certainly exceptions to the rule. There are times when atmospheric rivers can impact California even during a La Nina. In fact, the very weak La Nina 2016-17 concluded with several heavy rainfall events in January into February of 2017, which helped reduce the drought. And I think that's what I've got for these slides.
Great. Thanks so much, Michelle. So another major factor in California's drought story is its water management. And now Amanda is going to walk us through that section of the story map.
Great, thanks, Alec. You want to scroll down a little bit for me? Here we go.
Sure, just tell me when it's not.
Yeah, this will be good here. So in California's watersheds, obviously water management is this delicate balance between allowing water to flow downstream to control possible flooding, but also storing water for use during the summer. And this water is managed locally, and ideally the local, state, and federal agencies work together to collaboratively make sure all of California's water management objectives can be met, such as this water supply, hydropower, flood control, recreation, environmental stewardship. And this has inspired a couple different few strategies in this last drought, including that of information that was needed to make better decisions throughout the drought, including a tool from the Southwest Fisheries Science Center of NOAA that actually looked at temperatures to aid fisheries management, and also a collaborative management strategy called Forecast Informed Reservoir Operations, which is still going on and assessing its viability into that type of program. Obviously, conservation is a key element to California's water management as well as groundwater management. Al, if you scroll a little bit down, let's pass the satellite image. You can see over time, we can see here from the USGS that groundwater storage has changed and has decreased over time. And this came especially important in the last drought. And if we scroll down to the Grace image, we can sort of animate how that changed over time. So we can look at this on the ground, such as the Department of Water Resources does, through airborne observing, such as they do with NASA, looking at the San Joaquin Valley land surface subsidence, and also by satellite. And here's the NASA GRACE instrument, the Gravity Recovery and Climate Experiment satellite, which also helps us watch and see how these different ground level or terrestrial water storage changes have been occurring in California with time. This satellite detects fluctuations basically in Earth's gravitational field, and those are associated with the changes in the amount of stored water and give us this bigger, broader view as well as the localized view from DWR to look at this. And with that, Allie, I don't think we need to take too much more time on water resources. We can go ahead and let the folks get started on the progression of drought. This story map moves on then to look at how the last drought went through, and I'm going to pass it back over to Allie.
Thanks so much, Amanda. So yeah, as Amanda mentioned, now that we've covered some of the background of the story, Dennis is going to walk us through how the California drought progressed from 2011 to 2017. So Dennis, are you there?
Yeah, sure, I'm there. Actually, you know, I think it would be helpful if you backed up to the visual you were looking at with the reservoirs, because there's a point I think can be made from that. In terms, yeah, keep going back up that one, yeah. So it turns out from the standpoint of hydrology, and going back even further than this visual does in 1970, you see that big trough there, the first one in 76, 77. That kind of was the granddaddy drought going into the but before this one occurred, and if you look over to the more recent one, whenever you want to say that ended, given the strong winters, precipitation 2016, if you believe the reservoir storage, you can see where the trough is there. But you see the reservoir storage never went quite as low as it did in 76, 77, but the period for which it's low is longer, like about double or so. And that's kind of a characteristic of this particular drought as it evolved going back to 2011 or so. If you want to flip down now to where you're actually going to have me start, and I'm not sure which visual you were going to show. Yeah, that's the drought in the week August to this, and beforehand I was just flipping through it, and the storyline essentially for the drought starting in 2011, it was kind of insidious where you looked at the areas which is labeled beginning of the drought, and you see kind of yellows in there, which I assume are D0, which is kind of the least severe drought category. Started to creep in a bit in 2011. There's a little bit more in 2012. It actually goes back and forth. I mean, the thing about droughts is they don't, it's not like you just look at one thing and then it continually, you know, it's not like a stream flow hydrograph where in flood stage it just keeps going up and up and up. And then winter 2013-14 came along, which was a pretty dry winter. We did some work looking at that because that was when by 2013-14, it's some comparisons with the 76-77 one, and it's like, yeah, it's close. But we even wrote a paper on this. It's close, but it's not as big a deal as 76-77 one. Well, we wrote the paper about a year too early because then winter 2014-15 came along. And that's the one where the snowpack was record low. It blew by 1977, which was the previous snow drought of record, going back to, you know, these snow courses. There started to be a fair number of them in place by like the 30s and 40s. So the period of record is like 70 years or so, and 77 was clearly the granddaddy. Well, it wasn't anymore after 2015. I think the other interesting thing about the most recent drought, and this is still very much a discussion of evolving science, but the role of temperature. Okay, so if you look at that 76-77 drought, the precipitation was exceptionally low, but the temperatures were about average. Now, the one problem we have is, what does average even mean anymore? Because over the last, 70 years or so, there's been almost monotonic progression in the temperatures as they become warmer. You know, 77 was sort of the midpoint of that record, and it was about average for that. 2015 and the previous winter as well were exceptionally warm, and we continue to see that even in Dan's outlook and recap of the last winter, where temperatures were anomalously warm, but I'm kind of wondering, well, they're anomalously warm relative to the historic record, but are they the new norm? And what happens is, if you look at the water implications and you sort of look at the relationship between precipitation and, say, runoff, there's a very strong correlation. You just do a scatter plot, no big surprise. You get R-squareds of like 0.7, 0.8, stuff like that. If you do it against temperature, there's a lower correlation, and it goes the other way. The correlation's negative. High temperatures, low runoff. It's not as strong as with precipitation, but there is a relationship there, and we're sort of entering new territory here with these warm droughts. Another way of looking at that, there's work by Amir Agachek at UC Irvine, who wrote a paper showing that when you consider both the precipitation and temperature, the drought characteristics of those most recent one are by far the most severe of the instrumental record, going back probably 100 years or so. So I think I'll stop there unless you had other comments you wanted me to make.
That's great, Dennis. Thanks so much. So given this story of this drought's progression and significant impacts, we want to ask the question, what were some of the driving forces behind this exceptional drought? To talk about some of the causes and the role of climate change, we have Marty. Marty, are you here?
I am. I was hoping you had forgotten about me.
Sorry, you're out of luck.
So causes, and I think Dennis had just touched on some of the points, and Michelle also, because some of the causes relate to factors that were in the oceans and that distinguish the climate of today from the climate of a century ago. And here you see, for example, a couple of time series. The temperature one is the one really that Dennis just called out. It's remarkable since actually year 2000, if you do a statewide, very few, if any, of the years, the temperature has been consistently warmer than normal. And of course, during this drought period, it has been very warm. Statewide, the temperatures have been about 1.5 to 2 degrees Celsius warmer than they were in the first couple of decades of the 20th century. I'm going to come back to that in just a minute. But I wanted to go back and say, you know, in a cause-effect world, if we know the causes, then we can predict the effects. It seems pretty simple. So, you know, as I try to chat with you here about how I understand the science that's been done by many people on the question of the California drought event as to the causes, I want to caution that by speaking to certain causes, we may not be speaking to being able to predict the end product. At the same time, you know, if everything was just a matter of chance, if all of the meteorology that came about that created this 6 or so odd years of drought, then if it was all just bad luck, then risk management would be a rather meaningless exercise also. But we're going to find ourselves somewhere in between, where the science of climate and hydrology can speak to some factors that we can see in advance as causal agents. But at the end of the day, we're really speaking about a probability of how such agents could cause an outcome to be as severe as it was in these last 6-7 year period. And of course, the more extraordinary the event, like the drought, the greater is the need for us to be able to speak to the causes and to provide some strong proofs that causes indeed were foreseen or were at play. We heard the effect of El Nino and La Nina, and here we have it coming up again. In this period from 2011 to 2017, the ocean, this is a nice animation, you can see was prevailingly in a cool, these blue colors were prevailingly cool in the tropical, but you'll see that primarily there was a coolness. Now, this is not the whole period animation. This was one of the early years that kicked things off. But for the period as a whole, the ocean was somewhat cooler in the East Pacific. And Michelle had already spoken to how that predisposes a Southern California region, at least, to be drier than normal when the ocean is cooler than normal. But that's not really what drove the drought. I mean, at the end of the day, what really mattered was it simply didn't rain very much in the northern part of the state. So coming back to causes, a word of caution. And this is sort of against a tendency to assign a particular cause to an outcome like this drought, when in fact, it's only the laws of probability that are at play. And that's why the seasonal forecast that the Climate Prediction Center puts out is a probability forecast, right? And sometimes causes, even for a radically strong situation like in 2011 to 16, can involve rather minute disturbances. It could be just a matter of a couple of storms shunting into Oregon and Washington and missing Northern California and the Sierras. And having that occur a couple of years in a row could make all the difference between enough and not enough water. And so it's the sensitivity to these rather minute situations that also explains why meteorologists have somewhat limited success in predicting the weather. It is the sensitivity to small causes, and these small causes are not easily foreseen. I mean, it's sort of like many people will not blink an eyelash, and they'll think it quite natural to pray for rain, as they did during the drought, but they would think it rather ridiculous to pray for an eclipse, because an eclipse is extremely predictable. Rains are less so. And we heard, for instance, about a ridiculously resilient ridge, and we had an image up here just a moment ago about the weather pattern. There you go. This is just an example of the flow in the atmosphere. Actually, this particular image shows a pattern that would be indicating low pressure off the California coast and high pressure in the Intermountain area. But during most of the years of the drought from 2011 to 2017, the wind pattern in the Eastern Pacific had a consistent high pressure, anomalously high pressure, and it shunted those storms well to the north. And therein was sort of the most immediate cause for the drought, in that you had persistent high pressure, and the storms that normally brought rain simply didn't occur. You know, there's some numbers that are pretty remarkable when thinking about California water supply and drought. For the state as a whole, and these numbers are in the units of million acre feet, if those mean something to you, but it's the relative breakdown that I think you'll find interesting here. The state receives about 200 million acre feet of precipitation from these storms that come ashore, mostly during the cold half of the year. About 200 million acre feet of water is available. But nature right off the bat takes over half of that away. So nature already sort of puts us in a state of barely having enough water to do what we wish to or be able to do in the state. It evaporates about 110 million acre feet. So at the end of the day, only 90 million acre feet are available when the precip is of the normal variety. And of that water, when it comes to thinking about drought, of that water, only about half of that actually is available in ag and urban. The other half basically finds its way back into the sea or sits in the environment where it's not regulated or easily controlled. So when thinking about drought, there are sort of two aspects I like to think about, especially in this extreme event we just had. It's the magnitude of the water that's demanded. And, you know, it matters as to whether your exposure is that you need water for an alfalfa field, which has a very high water need, or if you're growing lettuce and broccoli, which has a much lower water need, you may find that you can get by with less water in one case than the other. And so your impact of the water supply being somewhat deficient may be different depending upon your particular need and your demand. The other one is the reliability of delivering the water. So come back to the atmosphere. So we had a drought because we didn't have the normal rains. That goes without saying. I said it anyway. And the rains didn't get delivered because we had high pressure off the coast of California prevailingly. And in part, those pressures were abnormally high for reasons that Michelle talked about, because the oceans were abnormally cool. But that would only explain part of the situation, and a significant fraction, more than 2/3 of the deficits and rains, simply didn't scale with how the oceans were behaving. So I would say we're rather unpredictable. It was the bad luck element in the storyline that we have to share here. So there's the atmosphere delivering the precip. Now, climate change came up as a question. So I'm going to jump a little bit. For California, especially when they're looking at Southern California, their water supply depends upon water that comes from the north. Thinking metropolitan water, LA, something like 2 million acre feet comes from the California Water Project. Another 500,000 acre feet comes out of Mono Lake area, the LA Aqueduct. Something a little over 1 million acre feet comes from Colorado headwaters through the Colorado River system. And then local precip that falls in the LA Basin and groundwater. In fact, groundwater, which we saw being depleted, is actually used every year to take care of agricultural needs in the state, especially the almond nut growing industry. Really depends upon groundwater, even in a good year. Something like, I think it's about over 20% of the water used in the state is sourced out of the ground. So climate change, well, Dennis made the point, it's been about 1 to 2 degrees Celsius, 3 to 4 degrees Fahrenheit, warmer than normal in recent years. And although we don't know exactly the effect that those high temperatures are having on the water resources, a couple of things we do know. Snowpack is not as abundantly built, so the storage in the high elevations is reduced. That affects the timing of the water that rolls into the streams and is held in reservoirs. And that wreaks havoc with management of water to time it right with when you need it in terms of agriculture. That's one aspect. So even if the total amount of water wasn't affected by the higher temperatures, which it is, it still would cause an effect in terms of timing and thereby could create drought conditions because when you demanded the water, it's just not there. The other aspect is the temperatures being as warm as they are. As I mentioned, under normal conditions, over half of the precip that falls in California is lost to evapotranspiration. Roughly a 2 degrees C warming as a back of the envelope would be expected to increase evaporation by something like about 1 to 2% is not an unreasonable number. It's not 10%, it's not 0, but it's in the single digits. So let's just play with this number for a second. Let's say that the higher temperatures have evaporated 2% more of the precip that falls in the state. Well, that amounts to about 4 million acre feet. And that additional temperature stress on the water resources is equal to the whole volume of the Colorado River Water Agreement that is supplied to the state of California. So one way to think about the temperature effect that really matters is in the magnitudes of the warming we've experienced, it's not unreasonable to suppose that the equivalent of a Colorado River water supply to California has been lost in the recent decade. Now that is made up by taking more water from the ground because agriculture still is chugging along. Agricultural productivity is still high. Even during this drought, the amount of productivity was remarkably high given how extreme the meteorological situation and hydrologic situation was because they could tap into the groundwater. Really, it was the groundwater that provides the buffer. And of course, that leads to new challenges. And I'm going to hand it back over here to Allison and Amanda because the groundwater is an interesting part of the story going forward, I think.
All right, so Amanda, I think it might be a good time to bring up the poll results. Marty, if you want to take a look at these results here and react to this a little bit.
I'm surprised that
poll open for a minute and a half and only 52% voted, so we didn't quite capture everyone's feeling on here. But
that's more than voted in the election in 2016, isn't it? It looks like, I mean, I'm surprised. 50% are saying that the drought hasn't ended for them.
Mm-hmm.
And I wonder whether they're saying that the drought hasn't ended, Amanda, or whether their concern and their risk exposure to drought hasn't ended, which is certainly true. The risk of drought is always there. So I'm wondering how they interpret that particular sentence.
Mm-hmm.
I find that one really interesting to chat about more.
Yeah. And so we want to end sort of the story map pull through with this, because obviously last year we had a very large wet year and snowpack and precipitation and dealt with flooding issues. At the same time, we were dealing with drought, and we're still hearing many different impacts, and as Marty was saying, risks that are still out there for drought in different areas. And so that's what we wanted to sort of end with this poll, so it gave us a sense to think about moving forward with research and questions that we're asking. And Marty, I didn't know if you want to add anything to that, but that was sort of the reasoning for having the poll, and that's an interesting result and gives us a lot to think about going forward.
It really is. Again, the groundwater provides a buffer when the in-stream, the surface water supply is being taxed. I think in 2014, if I remember right, they zeroed the delivery of water from North to Southern California in the Central Valley project, which, that's a big hit to be told that, hey, that supply of water isn't going to be available. Obviously, when people turn on their taps, water was always there. Municipal and industrial use has become more, I think the word is more extractive, but it is very efficient. And so the actual consumptive aspect of water use in municipal and in your homes is really rather small and hasn't risen that much given the population change, but it's become more intensive. It's really ag at the end of the day. The fields were fallowed, something like over 500,000 acres of fields were fallowed, alfalfa in particular, and cotton and rice were fallowed. But where people had access to water, if they had groundwater access, drought was not nearly so severe. There may have been a cost element to it, although I think there's a quote that I saw from a economist at UC Davis that said, during times of drought, what was it? If you can get to water, a drought is a great time to grow crops. So if the in-stream water is not there for you, but you can get it from the ground, and there's no laws against that or regulations on it, then, hey, it's a great time to grow your crops, in part because market forces do drive prices, and there's a lot of economic aspects we haven't even talked about that really determine whether drought is having a big effect. It depends upon the economic factors in many ways.
Yep. All right. Thanks, Marty. We're past the hour now, but I do want to give everyone a chance to ask questions of our speakers if they'd like to stick around. Go ahead and type those in if you have them. While they're doing that, I just want to say first, thank you to all the speakers for being on here today, and to Allie for putting together this great story map, and to Dan for giving us the update on the current drought conditions. I have here where you can find the story map out, and I will send it also out in the post-webinar email. This webinar has been recorded, and you can find it on drought.gov and the MAP website later on. And I'll also just mention that Allie pointed out the MAP website and the Drought Task Force, where you can find a California drought assessment and a recent drought and temperature assessment if you'd like to learn more about these topics that Marty and Dennis and others were talking about and learn about. Allie, is there anything you'd like to add?
I think you pretty much covered it, Amanda. In addition to being on the MAP website, this webinar recording, we also have a YouTube page. And so those videos and link to the YouTube page will be embedded on our website too.
Great. I don't see any questions coming in, so I can go ahead and end here. Our next webinar for the Drought and Climate Outlook for California, Nevada is scheduled for July 23rd, so we'll talk to you guys next time. Thanks, everyone.
Thanks.
Thank you.